All right. So, hello everyone again. Welcome to today's session on Water Talks number 22 by International Center for Clean Water. I am Pooja and I will be moderating the session for the day. We at ICCW believe that creating awareness about the crisis in water sector is a very important mode of accelerating change and influencing people and organizations towards water positivity. Thus, began a series of online sessions named Water Talks, creating a platform for interaction to bring about knowledge sharing. Our topic for today is non-revenue water reduction in water supply networks, and we will be hearing from our expert speaker for the session, Mr. Gary White. To begin with, let me introduce our advisory board member, who is also a dear colleague and friend to Mr. Gary, Mr. Ashok Natarajan, sir. Retired as the CEO of Tamil Nadu Water Investment Company, he has 37 years of rich experience in the energy and water sector, along with an in-depth understanding of challenges in its technological applications, contract structures, business models, risk analysis. We welcome you, sir. I humbly request you to preside over the session and introduce our guest speaker for the day.
Thank you, Pooja. I'm audible?
Yes, sir, you're audible.
Okay. Thank you very much for this opportunity to introduce my dear friend, Gary David White. I know him for the past 25 years, JVP partner, mentor, colleague. We have participated in those early days in Karnataka, modernization in Mysore, Pune, so many other projects across the country. He's been a visitor to India and understands Indian utilities very deeply. Gary runs his own company now called Water Consultants based out of Malaysia. And he's got a very, very good team of NRW engineers who have done lots of work in the states like Kontan and other big work. He's actually a master's in engineering, plus his special areas are in the areas of non-revenue water loss reduction, hydraulic modeling, and advanced pressure management. He has started his career with Bywater, then subsequently moved into various international operators. He's actually a Britisher by origin from Dorset, but now lives out of Thailand. And the last 30 years he has spent in Asia, primarily in Thailand and Malaysia, which is his home. He's got a wife in Thailand. And he has been very well versed with the Asian operations and typically developing countries' environment, and has a very deep understanding of India itself. He started his career, as I said, with Bywater, then moved into Subic Water, then into Thames Water. Then he moved into Ranhill Utilities, one of the largest utility operators in Malaysia, ran their entire concession and the non-revenue water loss program for many years successfully. Then he actually diversified into other sectors, but he's got a very, very wide understanding. He's also authored a number of books, and today he's playing a very key role as a secretary for the past decade as the secretary of the International Water Loss Association, which is the nodal body on whose water balance only every textbook or every utility operations is based on. So he's a key person in that. And I've been working with him quite closely for the last so many years. And I welcome you, Gary, into the relationship with ICCW, and also to relook at India. I know you have been trying very desperately into India for the last 25 years to bring about reforms and the understanding of non-revenue water loss. And I leave it with you, Gary, to take it forward. I'm sure I find that there are good audience here who are themselves solution providers who would like to take your advice and learn a lot of things from you. Over to you, Gary.
Okay, thank you very much, Ashok, for that introduction. Let me just start sharing my screen. Can everybody see that?
Yeah.
Yeah, okay. So as mentioned, I'm going to be talking today about non-revenue water. And in particular, I'm going to talk about what is non-revenue water, and also then go into more detail on what we would call the non-revenue water balance, which is basically breaking down the total non-revenue water into various components of non-revenue water. So let's look at what is non-revenue water. Basically, in our utilities, we have water treatment plants that are taking raw water and cleaning it. And when they do that cleaning process, they're expending money, and that money in terms of electricity to run the plant, chemicals to put in the water to help clean it, and also the staff costs for running the plant. So there's basically a cost per cubic meter of water, of each cubic meter of water that's being treated at the treatment plant. And then at the other end, or we would generally put flow meters on the outlet of our treatment plants so that we can actually measure quite accurately how much water is leaving the plant itself. And we would call these, often we call them bulk meters or system input volume meters, but generally they're there to measure accurately how much water is being treated. Then at the other end of the system, we have a series of customer meters. So in most countries, we would hope that all of our customers are metered so that we're measuring accurately how much water they are consuming. And then those meters will be read on a regular basis, and the customers billed basically for the water that they've used. So we've got two cost elements that we're looking at. One is the cost of treating the water coming out of the treatment plant, and the other cost is the amount of revenue that we're getting back from our customers. So there's actually a sort of very simple formula for non-revenue water, which you can see here, and it's system input volume minus billed volume. So that means the volume of water which is coming out of our treatment plants minus the total volume that's being billed to our customers. And the difference you can see is going to be called non-revenue water, and that's because we're spending money to treat that water, but we're not getting it back as revenue. So basically, we're spending water that's being wasted. Just to give you a sort of like a little overview about non-revenue water, this is something that was conducted by a Japanese water research center back in 2016. So it's probably quite old data now. But and I wouldn't worry about the numbers because a lot of that has changed. But the key thing is you can see that non-revenue water is very variable. We can get some utilities that have non-revenue water down at 10%, as you can see here, which is in Japan. Not the whole of Japan, but probably Japan as an average. And then you can see that some other utilities have got more than 60% non-revenue water. I know a couple of utilities in Malaysia, a couple of the states in Malaysia that have more than 60% non-revenue water. There is a figure there for India, I noticed, which is 25%. I'm not sure how accurate that is. It looks like it was something that was just guessed, really, because there's another one at 25% and 30% for Vietnam and Nigeria. But what's also interesting is the worst one is Jamaica. Now, this is in 2015, and it was at 69%. And there's been a big contract in Jamaica for the last 5 years, which has been is basically a non-revenue water performance-based contract. And they actually have non-revenue water now below 40%. So it's not sort of like the end of it if you've got high non-revenue water. It is possible to bring it down, but you've got to work at it in small steps and take it a little bit at a time. It's not something that you could rush through, really. Now that gives you, that formula that we were looking at gives you non-revenue water as like a total for an entire system. So when you've got sort of like huge utilities like you would have in Chennai, then you're looking at an average non-revenue water across the whole of that system. And that non-revenue water is actually broken down into a number of different components. So for example, the meters on the outlet of the treatment plant. We mentioned that we put meters on the treatment plant to measure how much is coming into supply. But if those meters are inaccurate, if they're not installed properly or they're not maintained properly, then that can be an issue. Sometimes we go to utilities and we find that they don't have any meters at all, mainly because it's a cost factor. It's too expensive to put the meters on. Maybe they don't want to shut down the mains because of customer issues that way. But it's imperative that the meters on the outlet of those treatment plants are all installed and are as accurate as possible, so that we can get a really accurate volume of water coming from the treatment plant. You can imagine when you look at the formula, if one of those meters is inaccurate, it's going to have a big effect on the total NRW calculation, especially as the number of treatment plants and the number of meters at the treatment plants is relatively low compared to the customer meters that you would have in your system. Then moving into your transmission and your distribution system, you're going to have leakage, which is happening at a number of different places. You can have leakage on the pipes. You can have leakage on your valves, on your air valves. You can even have leakage in your reservoirs, both balancing reservoirs and service reservoirs. If they're not maintained properly, then they can leak as well. Overflow of reservoirs can be a big issue as well. If you don't have proper control of your reservoir levels, then once a reservoir gets full and the water just starts flowing over, you're going to get huge volumes of water that's just flowing into the drains. Then we have, moving into the billing side, we obviously have service pipes, and we also have leakage on the customer side. Now, in most utilities where you have 100% metering, any leakage on the customer side is basically going to be recorded by the meter, so the customer will have to pay for it. But that's not always a good thing, because you have lots of complaints from the customer. The customers want you to actually come and sort out the problem. So that can be quite difficult to have that customer side leakage. If you have a system where a lot of the customers are not metered, it becomes even worse, because you've got a lot of leakage on the customer side, which is not being metered, and so becomes almost a responsibility of the water utility as well. Now, generally with your customers, you would have a lot more customer meters than you would have bulk meters at your treatment plant. Sometimes in the millions of meters for your customers. And so it becomes less important for those customer meters to be totally accurate or extremely accurate. But what you're looking for is an average accuracy across all of the meters that you've got in place. So these customer meters actually have a lifespan. They're mechanical, so they do have bearings and moving parts which can wear down. So you need to be looking at when you replace those meters. So you can see, based on this, there's there's lots of different areas that need to be considered when you're talking about non-revenue water. It's not just jumping straight in and saying, okay, let's go and do some leak detection, because leak detection may not be the issue. I remember working in the Philippines where they contracted me, this is in Subic water, they contracted me because the non-revenue water was at 46%. And when I turned up at the office, they basically had recruited 2 teams. They bought a lot of leakage equipment and they said to me, okay, go out and train the teams and find the leaks. So for the first 2 weeks, we went out looking for leaks with the leakage equipment, and we didn't find one leak in 2 weeks. And I'm like, there must be something we're missing here. So we then stopped and we started to do a water balance like we're looking at here. And what we found was that Subic was an old American naval base, and all of the meters were in US gallons, but they put in a new billing system that was in cubic meters or liters. And so all of the volumes were just totally wrong. And when we sort of went round and we fixed the problem, we did a meter survey and we fixed the billing system, all of a sudden the non-revenue water went down to about 14%. And it was almost like job done after a month. But they did keep me on to do a bit more work looking at their system. So the best way that we want to break down all of that non-revenue water is we want some sort of framework that's easy for us to look at and easy for us to break down the non-revenue water into the different components so that we can see where we've got the biggest volume and where we should start to do works to try and solve that problem. Now, fortunately, the International Water Association, the water loss specialist group of that association, they've developed a standard framework, which is called the IWA NRW water balance. And you can see that water balance here. So it starts on the left-hand side with system input volume, which is the meters coming from your treatment plants. We've then got authorized consumption, which is split into billed and unbilled authorized. And I'm going to go into more detail on a lot of these in a minute. We've then got the losses, and the losses can be split into apparent losses and real losses. So the best way to look at this is if it's real losses like leakage, overflows from tanks and leakage on your customer points, connections, it's where you can physically see water. So it's where the water is, you can actually see it. Now, apparent losses are basically unauthorized consumption or theft and customer meter inaccuracies. So these are actually, you can't physically see the water. It's more of a mismeasurement of the water that's being consumed. And then you would have your total non-revenue water, or a split between revenue water and non-revenue water on the right-hand side. So let's have a look at these different elements. So the first one is basically going to be system input volume. And as I mentioned, we tend to put very accurate meters on the outlet of our treatment plants. I would say the most common type of meter that people use these days are electromagnetic meters. There's a few reasons for those. First one is they're quite accurate across different flow ranges, from high flow to low flow. They are full bore, so you don't have any pressure head loss being created by the meter as you would do through mechanical meters. And they, because they're full bore as well, they're electromagnetic, then you can sort of easily connect them up to SCADA systems and get data that's coming back so that you can record those flow measurements. The other big benefit is there's no moving parts like you would get in a mechanical meter that's rotating. So based on that, you would expect your bulk meters to actually last a bit longer. So you would be looking at your meters to be lasting, probably more than 20 years as compared to a mechanical billing meter, which would be probably 8 to 12 years. You can see here, this is some work that's been done by ISLE Utilities in Australia, where they've done a bit of benchmarking for a number of utilities. And you can see that the average age of bulk meters is about 7 years in these utilities. But we do have quite a few utilities that are above that 7 years. So it just depends on a program that's been put in to manage those bulk water. One of the key things about these electromagnetic meters and ultrasonic meters, which are often used as well for larger diameter pipes, is that they need to have straight lengths of pipe upstream and downstream of the meter itself. And the reason we want to do that is because we want to try and get as nice as a flat or straight flow as we can and make it less turbulent. We don't want turbulence in the pipe. The reason for that is these meters have basically got these small sensors inside the pipe, and there's just 2 of them, one on either side of the meter. And what they're actually measuring is they're measuring velocity going past the sensor. And then based on that velocity that's being calculated, they then convert it into a volume or flow rate that's going through the meter. Now you can see if there was a turbulent flow, then we're not going to be measuring an average velocity at those sensor points. So you're going to get inaccurate flow readings. And it's the same it's probably even worse for ultrasonic meters. Because they basically are sending ultrasonic sound signals across the pipe. And if you've got air bubbles or turbulence in the pipe, it can actually cause those ultrasonic sound signals to go wrong as well. We really want to be connecting these flow meters to a SCADA system so that we're starting to measure the flow that's going into or going through the meter, so that we've got an accurate sort of like monitoring of the systems. The sort of things that we would be looking for would be these points of low flow at night. You can see it's actually increasing. So the question is it just an anomaly where people were using water that evening? Maybe there was football matches or something going on. Or is it a problem of leakage or pipe bursting in the network? These meters, they actually need to be verified quite regularly just to make sure that they're as accurate as possible. There's 2 types of verification that need to be undertaken. The first one is what we would call an electronic verification, which is just checking that the actual electronics in the meter are working as they should do. This used to be a problem maybe 20, 25 years ago. We used to have electronic drift in some of these electronic circuit boards, which meant they had to be recalibrated or verified on a yearly basis. It's not such an issue now. I think electronic circuit boards are a lot more stable. So probably once every 2 or 3 years would be good enough just to verify the electronics. But that electronic verification doesn't verify the volumetric. So what we often do is use a temporary flow meter, like an insertion probe here, or a strap-on ultrasonic, to basically verify that the volume going through the pipe is what's going through the meter. We would normally put the insertion or the strap-on ultrasonic downstream from this one, so it's not affected by anything that may be making this meter inaccurate. by doing these two checks, you then know quite confidently that you've got very good accuracy of your bulk meters. So then we move into the next part of the NRW calculation, which is your authorized consumption. And the first one is your billed consumption. So you would hope that you've got water meters on all of your customers. That's not true for some countries, like even the UK. So even the UK don't have 100% customer metering. This is something is a legacy, really, that in the past, there was no customer metering in the UK. It was all based on a fixed rate. So people used to get a fixed bill every year for their water, which was based on the size of their house and the value of their house. But the water utilities are steadily converting people onto meters, which will then give a much more accurate volume of what people are using, and it means that people then start to be billed for the volume they're taking, which is good. Some utilities will actually connect their meters onto these automatic meter reading devices, and this means that a couple of things really. One is that you don't have to have these meter readers that you can see here going round to every single meter and reading the meters, which would save on manpower and costs that way. But also with these AMR systems, you can actually start to get data more frequently, like daily data. And once you're starting to get daily data, you can also then start to make the data visible for your customers. So that means a customer can actually log on and start to see how much water they've been using for the last day or the last 2 days or week, whatever. So it does help customers to get a better visibility of how much water they are using, especially if a leak occurs in the property, then they can get a warning saying your consumption has shot up, there must be a leak in your house. Can you please go out, start to investigate it and fix the leak? Large customer meters. So these are the customer meters that are supplying industry, commercial, hotels, all of those sort of big businesses. And they actually will use a lot more water. I was doing a project with IS Selangor in Malaysia. They've got 2.5 million customers. And we looked at the top 1,000 customers. So 1,000 out of 2.5 million, and that accounted for 22% of their volume of water that they were supplying. So sometimes these large customers can be using a huge amount of your water supply. So it's even more critical that these are actually being measured as accurately as possible, and then be on some sort of SCADA or telemetry system as well, so that if they stop working, you get out there and you fix it or replace it as quickly as possible so that it doesn't affect your revenue. And probably it's even bigger issue because often utilities will charge more to industrial or commercial customers. So not only are they using a majority of the volume, but they're also an even bigger majority of the revenue that's being charged to the customers. So we move on to this unbilled authorized consumption, which is quite an interesting concept. So we've basically got unbilled metered and unbilled unmetered. So the unbilled metered is basically where you actually have a meter on somebody so that you actually know how much water they are consuming, but you don't bill them, which means you're giving them free water. Now, this can often, when we look at utilities, it can be a very small amount. For example, I was working in Laos recently, and most of those utilities, the free water is actually the water utilities' own offices. So it's a very small amount. But there can be some utilities that actually have a very huge portion of their customers that get free water. For example, in Brazil, in Sabesp, which is Sao Paulo, all of the water that goes to the favelas or the slum housing is metered, but it's all free water. The same in South Africa. South Africa during the apartheid times, all of the black townships used to get free water. Now they want to start charging them for it, but the first step is to meter them, but people are reluctant, obviously, to pay for their water. The same thing in the Soviet Union. A lot of those Soviet Union countries, they used to meter customers, but they didn't charge them. They used to give them free water. There are some other ones like religious buildings, palaces and farms in the Middle East, and also water tanker filling stations. It's okay if you're going to give free water, as long as you are metering it so that you know that the volume of water that's being used by those customers, so that you can account for it in the water balance. What's a bit worse is when you have unmetered, unbilled. So this is where you have people that are taking water, but it's you don't bill them for it and you don't meter them, so you don't really know what the volume of that water is. And once again, this is generally a small percentage. I think the IWA says you can make an assumption of 0.5% of your system input volume, but sometimes it can be a very large component again. The sort of things we're talking about would be firefighting. So if the fire brigade, fire company come and connect to the water main and they start to take water, it's not metered. But hopefully you can make an estimate of how much water they are using. Flushing, mains flushing or sewer flushing. This happens quite a lot with utilities, especially also when you're putting in new pipes, cleaning of new pipes before they're put into service. There's a lot of flushing there. And so we do ask utilities to try and estimate how much water they're using in these flushing operations. A few others that are not common, but sometimes public fountains, street washing, irrigation of public gardens is another one. Sometimes these can be are not metered and not billed either. If you can, if possible, move some of these. So like irrigation of public gardens, if you can put a meter on and convert it into unbilled metered, at least you're getting an accurate estimate of how much water is being used in that component of non-revenue water. So we move now into apparent losses. So unauthorized consumption is, we call it unauthorized consumption rather than theft, because there is basically a number of different factors that can be part of this. Illegal connections, where people tap the main themselves or they disconnect the meter. Misuse of fire hydrants, where people actually use the firefighting systems or connect to a fire hydrant to fill up a tanker. Vandalism or bypassing meters is quite common, and also corrupt meter reading. So there can be occasions where the meter readers are not actually reading the meters properly, but they're what we call doing coffee shop meter reading, which basically they sit down and they put in any number they want. either because they're too lazy to go and read the meters, or because they're being paid by customers to not put in the true figures. Some of the big illegal connections can often be construction companies. So what we say to a lot of utilities is, if there are actually building sites, always check where those building sites are getting their water from. Make sure that they're connected to the main and that they've got a meter on there, so that you're measuring how much water is actually being used by those construction sites. These are sort of the illegal connections that we sort of see on a regular basis. You can see this one is actually, there used to be an air valve here on this S-bend, and somebody's taken the air valve off and just put a connection on so that they can supply water. It's a big pipe as well. These are actually illegal connections, illegal tappings under a bridge. And you can see how many of them there are with all of these pipes that are running around. So you can imagine what effect that's having on the pressures and flows in the network caused by all of these. These are illegal bypasses. You can see here that this is a bypass around the meter. And I don't know how this one thought they'd get away with it, because the bypass is about 4 times bigger than the actual pipe going through the meter. But quite often these bypasses can be buried. So you don't actually see this bypass pipe, but you just see the meter above ground and you think everything's okay. Missing meters. Now, quite often, this often happens when a customer doesn't pay their water bill. And so the water utility then goes and disconnects the customer, takes the meter away. And so that the customer then has an option to go back into the water utility, pay their outstanding bill, and then they would then get their meter back and they can start charging water again. But quite often you'll get customers that think, I don't want to pay my bill, and it's probably easier if I just put this bypass or this illegal pipe where the meter used to be. So with utilities, it's important that when they do disconnect somebody, that they actually go back and they start to analyze or check the customers that haven't come in to pay their bill. So go to find out, how are they getting water? If they haven't paid their bill and they've been disconnected, how are they getting water? Because 99% of the time they'll have put some sort of illegal connection like this in. This is the fire hydrants that I was telling you about. This is actually Australia, this first one. And firefighting systems in Australia are sort of like a separate supply network, and they're not metered. So you can get a lot of people that use the firefighting systems for cleaning car parks or cleaning outside. And then because it's not metered, the utility doesn't know and they don't charge them for it. And then this is a fire hydrant where somebody has put this tapping on and they're sort of like taking the water for some reason or other. Now, as I mentioned, these customer meters, they're mechanical and they've got moving parts inside. So they've got bearings and they turn. And over time, they basically wear out. And what happens is they start off accurate, and then they slowly start to drop their accuracy until it gets to a point where they'll just eventually just stop working. Now, some utilities will just run them till they die. But the problem is that they're going to be very inaccurate for a period before they die. That could be 3, 4, 5 years before they die, that they're actually quite inaccurate. So what's recommended is that utilities actually take a sample of their meters, take them from different ages, 6 years, 8 years, 10, 12, 14, and you do some lab testing on a proper meter test bench. And you actually can then determine when the meters start to lose their accuracy and become a revenue loss to the water utility. And quite often it's around between 8 to 10 years normally, but it does depend a lot on water quality, the hardness of the water, iron in the water, any sediments in the water can affect the accuracy of the meter or the lifespan of the meter. If you look here, this is that benchmarking I was telling you about from a few utilities. I think they're Australian and UK, most of them. But you can see the average is about 10 years. Most of them have got below 10 years, and there's a few that are a bit higher. This utility, their meters are about 20 years average, but they actually did the testing that I mentioned on the test bench, and they found that their meters were still pretty accurate up to 20 years. So they were quite happy to have their meters carrying on at that age. We've done a lot of meter replacement programs in Malaysia and other countries, and we can see big impacts of revenue increasing, 10 to 20% replacing meters. So not only does it affect non-revenue water with the accuracy of your meters, but it also affects the revenue. Increasing the revenue from the water utility really helps to then have money to spend on other non-revenue water programs. So by doing that, what we've done on those different elements there, we get the real losses sort of drop out. So we take system input, we then deduct billed authorized, we deduct unbilled authorized, we deduct apparent losses, and what's left is the real losses or the leakage. And we actually call this the top-down approach, which basically means we start here and then we work down to get our real losses. But the volume of real losses depends on how accurately you estimate these volumes up here. And quite often utilities will actually underestimate some of these issues here. And that's why we then start to look at a bottom-up approach. And the bottom-up approach enables us to verify the volume of real losses, but it also helps us to break down the real losses into leakage on transmission and distribution, leakage on overflows, and leakage on service connections. We do that through the establishment of DMAs, district metered areas. So what we're looking to do is we're looking to divide the network into smaller, manageable zones. Generally, these DMAs, these district meter areas, are between 1,000 and 2,500 customers. So some big utilities can often have hundreds, if not thousands, of these DMAs that are sort of like installed across their network. The key thing about these DMAs is they have a flow meter. And that flow meter is actually measuring the flow into a single DMA. And this means that because you know the customers that are in this DMA, you can actually do a water balance or an NRW calculation first, and then a water balance for each DMA. So instead of now having NRW across the whole of a system, a huge supply system, we can now break it down into smaller units. We can do NRW breakdown for each smaller DMA, and we can then start to prioritize where we manage our non-revenue water or leakage in there. But what we can also do is we can start to do flow balances. So if we've got a meter on the outlet of a reservoir or a treatment plant, and it feeds into the trunk mains or transmission mains going down here, then if we subtract all of these DMA meters off, then what's left is telling us that it's the leakage in the trunk main. So we can now do an estimate of trunk main leakage. We can also estimate leakage or non-revenue water in each DMA as well. We can also look at the breakdown between water main leakage and service connections. Generally, this is done using historic repair data. So if you have a utility that's found a lot of leaks on their mains pipes and their service connections, we can actually work out how many mains pipe repairs there were, how many service pipe repairs there were. And we can then do a calculation where we can actually break the volume down between distribution leakage and service pipe leakage. This is actually real data. This is a utility in Australia called Unity Water on the Sunshine Coast. You can see that they believe their reservoir leakage is very small. They've then got about 11% trunk main leakage and about 32% reticulation main leakage. But that means that the majority of their leakage is actually on the service connections, the tapping from the main going to the customer meter. And what we're finding in a lot of utilities is that service pipe leakage is often a very big component of non-revenue water, mainly due to poor quality of materials. People are using cheaper materials for their service connections, poor quality installation. They're not burying the pipes deep enough. They're not using sand surround to protect them. And a bit of a lack of maintenance in managing those services as well. So that enables us to basically do a real breakdown of non-revenue water using the water balance. This means that we can then look through each of these different components and we can identify which one has got the biggest volume. So it could be that leakage on service connections, as I just shown here, could have the biggest component. This means that you can then say, okay, that's fair enough. Let's now do a program of leak detection on our service connections, or even just replacement of our service connections with better materials and better installation policies. It could be that your biggest component is this one, customer meter inaccuracies. It could be that your meters are very old and very inaccurate. So by replacing meters, replacing customer meters with newer, more accurate ones will help to bring down your NRW more quickly. But it will also help to increase your revenue as well. So it's quite an important way of sort of like breaking down the NRW to help you then move on to the next step, which is developing a program of non-revenue water management. Now, percentage, a lot of utilities will use percentage to sort of report how much their NRW is. And I did show you a chart at the beginning, which was from the Japanese, which basically showed those different countries in percentage. But percentage is not a very good way of reporting non-revenue water. Basically, you can get variations because the customer data, the billing data, can vary greatly month to month. It can vary due to the number of days in a month. It can vary due to the weather. Obviously, in hotter weather, people will start to use more water, so NRW will go down as a percentage. The same with national holidays, where you've got people using more water in national holidays or staying at home. So these can affect your billing volumes, which can then affect non-revenue water as a percentage. So one of the first things we do is to say, okay, if you're going to use percentage, that's okay, but instead of just doing it month by month, let's start looking at rolling averages. So probably the most common is a 3-month rolling average, or sometimes a 6-month rolling average. And that will tend to smooth out any of these variations that we get in the billing data. Also, rather than using percentage, there are a couple of other indicators that we would recommend that you use, especially for real losses, the leakage side. And those are liters per connection per day, especially for urban areas, and liters per kilometer of pipe per day for rural areas. And those will enable you to get a better feel of the volume of your leakage rather than a percentage. If you've got a volume, you know that if the volume goes down, that's because you've found leaks and you've repaired them. So it's much better to look at volume in volumetric terms rather than percentage terms. Now, there is a free software which was developed by a guy called Roland Limburger, I think when he was working with the World Bank. It's actually an Excel spreadsheet. So it's very easy to use. You can see this is actually a screenshot of it. So basically you work your way down system input, bill consumption, unbilled, and you can basically enter in the different data step by step. And then at the end, you actually have your water balance that's produced for you. You can actually download this software free of charge from this website that's up there, www.limburger.cc. So that would enable any utilities to actually be able to develop their own water balance and to start to then think about where the data is difficult for them to fill in the water balance. So for example, when you come to system input volume, if you then find out that some of your treatment plant outlets don't have any meters, you know, the first step is let's put some meters onto the outlet of our treatment plants. So that's the sort of thing that this water balance can be used for. Thank you very much, and I hope it's been an interesting topic for you.
Thank you so much, sir. Let me just, so basically Mr. Navanithan says, seems like it would make sense to meter fire systems and then have alerts when there is an unusually high amount of water being consumed through it. This was during when you were mentioning about the Australian, firefighting system, which did not have any metering.
Yeah, the reason for that is it does go back quite a few years, and at the time electromagnetic meters weren't so common, so most customer meters, and they still are mechanical meters. And so there was a policy with most of the Australian governments that they didn't want to put mechanical meters onto these fire flows because it would cause head loss, or it could cause an issue with the firefighting system. So that's why they left them unmetered. But there is a lot of talk nowadays, because of electromagnetic meters having full bore, of starting to put those meters on, so it's not going to cause a head loss issue.
Okay. So Mr. Bala has put in another question about most Indian water utilities have very few consumer water meters, up to 20 to 30%, except in Bangalore city. In such situations, how can it be estimated NRW to the particular utility?
Yeah, it does become very difficult, but it is done in the UK. As I mentioned, the UK doesn't have 100% customer metering. So basically, you have to start using a lot more assumptions. And we actually have an assumption in the UK, which is liters per connection per day or customer per day. And so based on the number of houses that don't have a meter, you can make an estimate of how much water you think they are using. This can be done through some metering, like a temporary metering, not every single customer, but you could do a sample of customers to get an idea of how much water people are using. You can then average that and use that for those customers that don't have meters on their houses. But in the UK, a lot of what people look at is leakage, and they're looking more at the night flow. So they're looking at water, how much water is going into an area at night, because at night you would assume that most customers are asleep and they would not be using water. So the water going into an area at night is a good indicator of how much leakage there is. This is, of course, if it's on a 24/7, a continuous system. If you're working with an intermittent system, it's a bit more difficult.
Okay. He also wants to know, this was at the about the strategy part, but he also wants to know what is the technology that can be applied for more efficient, water supply management system in controlling and maintaining good NRW.
Yeah, so there's a lot of technology out there. It obviously depends a lot on when you do your water balance. It depends a lot on what you find the problems to be. So if it's your treatment plant meters, as I've mentioned, putting some electromagnetic meters, which are good technology, with some sort of SCADA or data logger system on there, would be very good. Then we're talking about customer metering, and not everybody is metered. So putting metering on is obviously a very good step, because you'll start to get a better control of how much water is being used. Then dividing your network up into DMAs, as I mentioned, into those zones. And if we can put meters onto each DMA so that you're monitoring how much is going into a zone, then that enables you to get better visibility of each DMA. You can then start to look at things like pressure management. Pressure management does sound like a strange thing to think about if you don't have full supply, but there are a lot of valves out there, pressure control valves, that can actually fix the flow rate and fix the pressure. So you can actually feed water, a specific amount of water, to an actual area. So I know that I was working in Thane, just north of Mumbai, and there was there's a utility, or not a utility, but a water company called STEM, and they had a big trunk main, and they had a number of feeds coming off. And we actually installed some flow meters and control valves to actually open automatically, feed customers an area with a fixed amount of water at a fixed flow rate at a fixed pressure. And then after a certain amount of time, it closed off again. So there are some sort of technologies for controlling the pressure and flow. And then, of course, if leakage is a problem, there are actually devices out there that you can either manually go around listening for leaks, or you can put on some permanent leakage monitoring systems on there. The issue with leakage is you do need to have a pressurized pipe. But the good thing with intermittent supply is that when the pressure does come on, a bad thing is when the pressure first comes on, you're going to have the water comes on, you're going to have low pressure. So you've got to wait for that pressure to build up before you can then start to do leak detection accurately.
Okay. Our CEO, Mr. Nandakumar, has also posted that most of India is unmetered and unbilled. Moving to metering and billing will provoke people to find ingenious ways of beating the system. Are there any foolproof designs that can prevent such acts or give timely alerts as a de-risking measure?
Yeah, I mean, it used to be tampering of meters used to be very common. People would use magnets. They would put needles through the meter. They would take the head off and put the head back on again. But the meter manufacturers have got very much better at it now. And so the tampering of meters is not so easy to do. One of the things that we have in the UK is that customer meters, because in a lot of countries in Asia, the meters are above ground, and sometimes they can be in customers' property, sometimes they're outside, but they're above ground. So in the UK, the meters are actually in a hole in the ground. And so the meter reader actually unscrews the top, takes it off, and he can then look down at the meter inside. And so it's not so easy for people to do any tampering with the meter because it's not visible. They don't really know what's down there. So you've got to be thinking about not just the product itself, the meter, but how you install that meter to make it more difficult for people to access the meter or do anything wrong. Also, as I mentioned, there are some automatic reading devices out there. So if you were to bury the meter, you could actually put some of these automatic readers on there, so the meter reader doesn't even have to take the top off, it just sends the information. There are a few smart meters out there at the moment that actually can detect if anybody is tampering with the meter, and they can also detect leakage on the customer side, and they can report that. So they got a digital head. So it does sort of like not prevent people, but people, you can tell people, we know you were tampering or you were trying to do something. But it is an issue. Even in the UK, as I was mentioning, people are so, even though the water utilities want to move onto metering, people are just so anti-metering. There's a lot of people anti-metering. Even if it means their bill would go down, they still don't want a meter on their property. So I know what it is. It's a difficult thing, but I think it has to be done, and maybe education is a key factor in teaching people about what you're trying to do and to get them to measure how much water they're using accurately.
Gary, just to add to that point, Pooja, just a second. You know what the intent of the question was that there's so much body of knowledge that advanced countries have, whether it's UK or Australia or some of the other European American companies, on managing utilities for so many decades. So is there some list of best practices that are available at the IWA or any of the organizations which can be used for in India to say leapfrog some of the problems that we may encounter if we start doing it for the first time in many of the cities? You talked about high quality meters and whether they are underground or overground. So if there is a recommended set of practice, and there would be a cost to it, obviously, the quality of meters, higher quality meters may cost more, but at the same time, there is a trade-off between how much we invest in non-revenue water, prevent reduction, and what is actually the cost of leakage. So at some point, we may want to take a call and say, this is what we would like to spend and keep the NRW up to a certain level. And we achieve it to some extent. Obviously, as you said, education and other things are important. But we reach a level where we agree that this is the best we can do at this point of time. But we have a system, artificial intelligence is also there today, which can collect all this data and probably give us some alerts. So is there something that is available, or is there something that is happening that we could participate?
Yeah, we do have a series of guidance notes that were developed by the IWA water loss group. One of them is apparent losses, which is a big part of that is meter accuracy and customer billing. It's something that we're actually going through an upgrade at the moment. We're reviewing it and developing a new one, but probably within the next 6 months to 9 months, we would have something that we can release as a guidance note on that.
Yeah, thank you.
Okay.
It's 6:15 already, 6:12. So if there are any more questions, we can address it for another 1 or 2 minutes.
Gary, can I answer this question on metering by Mr. Nandakumar for a second?
Sure.
You see, there are standards for meter, for high quality meter. There is a standard called ISO 4064, which talks about what is called as the dynamic ratio, in terms of your minimum flow to your permanent flow, that Q3 by Q1, this ratio. And if these quality standards of ISO 4064 is concerned, India is actually, there is a very good guideline now coming out of CPHO itself, our Indian ministry, just studied metering contracts across the world, and I've understood how high quality meter improves the life cycle, how low Indian conditions of low flow, low pressure can be measured. So that is one of the things that is catching on today. And India, especially since we face this problem of low flow, low pressure, so people are started suggesting these type of manufacturing standards to meet the life cycle cost of meters, and also very rigorous endurance testing. Say there's a test laboratory called FCRI, which calls for life cycle test. And that is how the products that come out today are these EEC marked or ISO 4064 marked. Typically, people like Orissa and all have done this, and even parts of Bangalore and very many of the good contractors have done it, and it has given them good dividends. The life has improved quite a lot.
Thank you, Ashok, for that.
There is a big guideline on that, and you can actually refer to it. I'll send it to you.
Yeah, thanks.
I think some of the issues with metering is, when you have intermittent supply, there can be problems with the meter running backwards when the supply goes off. And then when the water comes back on, you've got air that's being pushed through the pipe, and that can be pushed through the meter as well. But then also, quite often when you have intermittent supply, you have people, they store water. So they would actually have big tanks and they store water or wherever. And then when the water goes off, they would use that water. But then later on, when the next lot comes on, they might throw away the old water. So they're actually using more water than they would do if they had a continuous supply. So there can be reasons why people are not happy about having meters on their supply. And maybe if it was moved to 24/7, they would actually get a more consistent meter reading and wouldn't be so unhappy about having a meter and paying for what they're using.
I think Moinak from Solinas wanted to ask you one last question, and maybe we can close up after that.
Sure.
Okay.
Hi, Gary. Generally, one of the reasons why we have high NRW percentage in India is because of the leaks that we have in the distribution line specifically. So, what's your take specifically from from Western market or from the place you are in Southeast Asia? How does this if we have these pressure sensors or meters, we can map out a segment. Okay, within this segment there may be a possibility of leak or some ferrules or some tapping through which the leakages is happening or stealing is happening. But from the perspective of this last mile pinpointing of the leaks, how effective is this technologies like helium and or acoustics based things that we have? How effective is it from your experience that you have been seeing from all over your career, specifically in the Western markets?
Yeah, so talking about the two different technologies you talked about there, the helium and the acoustic. I'll talk about the acoustic first. So basically with acoustic leakage, we're trying to listen for the leak as it's creating a noise. So it's basically if your pipe is under pressure, water is being forced through the leak. And as it goes through the leak, it actually dissipates the energy that it had, the pressure. And we're actually listening to that energy being dissipated. It's a bit like when you open a can of Coke, you hear tss noise, and that's the pressure that's being released when you open the Coke. Now, the noise that's generated by a leak, is not consistent. It can depend on the pressure in the pipe. It can depend on the type of leak, whether it's a sort of pinhole leak, a split, or a burst. And it can also depend on the material, because a plastic pipe will make a lesser noise than, say, a metal pipe. So you've actually got an issue, first of all, with the noise that's being created. What's best is if you've got high pressure and you've got metallic pipes. If like in India, where you've got fairly low pressures and probably a lot of AC and plastic pipes, then you're not going to get a very strong leakage noise. Then the next issue is the noise of the leak then has to travel along the pipe material, either the pipe material or through the water. And if you've got a weak leak noise to start with, it's not going to travel very far along the pipe. And plastic pipe and AC pipe is very bad at conducting sound. Metal pipe is a lot better. So it depends on your pipe material, how far the leak noise is going to travel along. So that means if you've got a lot of plastic or AC pipes, you have to put your sensors a lot closer together. And I'm talking, 50 to 100 meters apart so that you can hear that noise. There are some devices now that actually listen to the noise, leak noise in the water column. But to do that, you actually have to connect your devices to the water, which means you either have to connect to a fire hydrant so that you're listening to the water column, or you have to tap the main and connect that way. So in India, one of the biggest issues you're going to find is probably going to be the number of fire hydrants that you've got. So you're actually going to have to tap the mains to put these devices on. So that's what makes acoustics difficult. In a lot of other countries where we have 24/7 supply, we have good water pressure, and we have, I wouldn't say good materials, but we have more fire hydrants, then leak detection becomes a bit of an easier way of doing it. Now, using gas technology, that is used, but not many. It's sort of developed in France. It's used a fair bit in France, but not many other countries tend to do the gas detection. There's two options. You can either pump gas into an empty pipe, or you can pump gas in and mix it with the water when you've got supply. Now, when you pump it into an empty pipe, you actually need to use a hell of a lot of gas, and it's just not cost effective to do that. So you would want to do it into a pipe where you've got water that's going in. But then the problem is the gas is going to come up, and gas is quite light. So it can work its way, and it may not come to the surface directly above the leak, but it can work its way a long way down the stream. So what people do is they drill holes every meter in the concrete or in the ground, and then they sniff for that gas. So gas technology is there, but it's not a cheap technology. So it's a case of weighing up whether you go for a cheaper acoustic or you go for a more expensive gas. And the acoustic, you have to get the right conditions for it to be working accurately.
Thank you. So what see like how it is done in like UK specifically? Do they use this acoustic specifically?
In the UK, they would use electronic listening sticks, ground microphones. They would use leak noise correlators. They would use leak noise loggers. So, I mean, the UK, it's probably the worst leakage in the world. They have very bad leakage in the UK. So they have lots of technology and lots of skills for doing leak detection there. In places like Malaysia and Thailand, they use the same sort of equipment. They would use leak noise loggers, ground microphones, electronic listening sticks. So I think most utilities basically look at the basic stuff first, like a ground microphone and a leak noise, electronic listening stick. Then they would move slowly up to more advanced technologies.
Well, I think we are nearing the end of the session. I would like to take this opportunity to thank Mr. Gary for an informative session. It's truly critical that we all take responsibility to know our own consumption and regulate it with better utility measures. I'm sure it gave everyone some motivation to focus more on the water balance and invest in strategic planning of water management systems to ensure minimal to no loss of precious water. Special thanks to Mr. Ashok Natarajan sir for connecting us with Mr. Gary, making this session possible. And I really want to thank everyone for joining this session and for all the questions that people have asked, for all the interactions, and making this a very successful session. Please spread the word and keep your actions water positive. And we can conclude the session if everybody agrees with me on this.
Thanks, Gary. Bye-bye.
Thank you, everyone. Bye.
Bye.